Alrighty, so um, I did my project on the characterization of bismuth telluride, and bismuth telluride is a material with many interesting and useful properties. In particular, it's a very well-known thermoelectric used in many applications. One common one is in refrigeration. There's also ongoing research into using bismuth telluride in areas such as power generation. And one area that in particular interests me is solar power. And this study attempts to computationally characterize two-dimensional bismuth telluride to help set the foundation for future research into the material and its applications. So just a little bit of background on the methodology and computational details. Um, the characterization was performed using VAS, the Vienna ab initio simulation package, using density functional theory. And density functional theory essentially is solving Kohn-Sham equations, which is that first equation that I have listed there, to determine the total charge density, which is then used to determine the potential. And I skipped a few steps between those just because time and slide space, but I have the equations at the end if anyone's interested in seeing the whole walkthrough. So a little bit more details on just the computation. I use the projector augmented wave method to treat the interactions. The total energy calculations were performed using the Purdue Burke Ernzerhof generalized gradient approximation. There was a gamma-centered K-point mesh of 2525 by 1 to sample the Brillouin zone, cutoff energy of 220 electron volts, and the structure was relaxed until the change in total free energy between ionic steps was less than 1 times 10 to the negative 6 electron volts, and the energy cutoff criteria was 1 times 10 to the negative 7 electron volts. So after the relaxation, these were the structures that I got. No, the first image is a image of the structure relaxed at 0 Kelvin, and the second image is the structure. It's a snapshot of the molecular dynamics run at around 300 Kelvin, or at 300 Kelvin. And in that run, there's very little motion observed in the system because it's at a relatively low temp, and all of the constituent atoms are relatively heavy, so they don't move around that much, and it's a stable configuration. I have a video of the run here. I won't play the full thing because it's about a minute long and only have 5 minutes for the presentation. But as you can see, not much happens. It's stable and again low temperature, so it's not going to break apart or anything. But and so I'll just leave it at that and move on. Also, if you saw the atoms blinking in and out, and that's because one atom is moving over out of the unit cell, and then another atom is replacing its position. So they pop in and out as far as the visualization is concerned, but they're still there. And so after I did the molecular dynamics run and the relaxation, I moved on to do the momentum dispersion, which is just taking the HOMO and LUMO orbitals and plotting their energy at each individual K-point coordinate. And that gives you this picture of the momentum dispersion. And that lets you see like the gap between the HOMO and LUMO. And as you can see from these plots, the gap is centered at the gamma point, the 0, for ky and kx. And that means it's a direct band gap system. And between the anions, cations, singlet, doublet, and triplet, the structure doesn't really change much. The bands just kind of move up or down a little bit depending on the system, but the overall structure remains consistent. The density of state plots here as well shows you how again, anion, cation, +2 anion and -2 cation. Excuse me, backwards. But and then just singlet, doublet, and triplet for the neutral system. And the density of state shows that the band gap is approximately 0.51 electron volts, and we know it's a direct band gap as well from the momentum dispersion previously. And then finally, we have the oscillator strength, which is essentially showing you the absorption spectra. It's um, the strength of, or the relative probability of the material to absorb light at a specific wavelength shown here. And as you can see here, there are a few different spikes in the absorption spectra around 1 to 1.1 electron volts, and then 1.3 to 1.4 electron volts. There's some pretty strong absorption, which are both in the infrared range, which is to be expected for bismuth telluride. And so for conclusions, the optical and electronic properties of bismuth telluride have been characterized, and from the simulations it can be seen that the material has a gamma point centered direct band gap, approximately 0.51 electron volts, and absorbs strongly in the infrared region of the electromagnetic spectrum. And these results, along with others I didn't have time to discuss, are the first to help further future computational research into bismuth telluride. And thank you. And does anyone have any questions?
Okay, please join me thanking Boston